Welcome to the AI for You Cafe for live presentations around AI. I'm very happy today to welcome in the cafe Christel Tanek from Orange Labs, and with her talk on ethics by design in AI, guidelines and toolkits to develop fair and explainable models. My name is Carmen McWilliams, and I'm the moderator and organizer. I'm the director of the company Grassroots Arts in Germany and partner in the AI for You project. As always, shortly the rules. Please take notice the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speaker can express her personal view and opinion. This is not necessarily the official AI for You project opinion. So what is this cafe about? What could it be about? The cafe is an online forum to gain insights into the European AI scene. Participants can get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. Again, I welcome you all. Great that you're all here, and of course, great that you're here, Christel. Great that you are here, participants all around Europe and the world. And please, this is an interactive session. You have the chance after the presentation to ask questions. There's on the right side, there's a panel, and there you also see a chat for questions. You can type them in. I'm going to read them afterwards to Christel, and she may answer. So this is always the short introduction. And again, welcome to Christel Tanek. Hi, Christel. And I want to introduce you, and then it's up to you. Christel has been working in Orange Labs for 17 years. With a business school background, she has been involved in many projects: IoT, smart cities, data management platforms, ethics by design in AI. She always has an innovation management approach that considers technologies will enhance services for users. With fellow engineers, they have been studying for 18 months on the ethical issues that any data scientist can face during the construction of AI services and how to start using ethics by design methodology to support them. In spring 2020, the two colleagues, among whom a student from UPC School Barcelona, École Centrale de Nantes, France, they studied the different open source tools available to develop fair and explainable models. IBM Toolkit offers the most functionalities, and they studied in detail. This web cafe today will be an opportunity to share with you her analysis, exchange on what remains to be done, and share your practices. So now I am back to Christel. I will make you now the moderator. You can say hello and you can present as you like. And now I give you the moderator role.
Okay. Hello, everybody.
Yes.
Hello, can you hear me?
Yes. We can
yes,
hear you.
and you can see my slides.
Yes, I see your slides.
Yes?
Perfect. Everything is perfect. Okay. Looks perfect.
Okay. Hello, everybody. So my goal today is to give you an overview of what can be done when you are a data scientist to develop models, AI models, that will be fair and explainable. Later, if you want to go deeper in the subject, well, we can have an exchange, but after the web cafe. So I supervised the internship of Hugo Miralles, as Carmen explained, and so I was working with a colleague of me from Orange Labs too, Patrick Rohan. So, slide. Okay, so we will have we will see what can be done to develop fair model, and then what can be done to develop model that will be explainable. So first of all, we we put our study in the European background, if I can say, with the European vision of AI. I mean a trustworthy AI as defined by the European Commission. That means an AI that will respect laws, that will be robust on a technical point of view, and that will be ethical. So these are our motivations to conduct this study in order to strengthen ethical values and social issues too. The position we adopted was to have a bottom-up approach to be complementary with the top-down initiatives we can see. And we decided to focus on 3 main principles that the data scientists have to address during the construction and the development of his model: fairness, explainability, and reliability. By fairness, we mean an algorithm that will produce the same outputs for anybody, and that will not discriminate somebody, and that will not be biased for any kind of person or group. We will see that in details. Explainability means that the output of the model must be understandable by anybody, depending on his background. Well, whatever his background, the person have to understand the decision made by an AI model. And reliability, well, it's a principle to be robust on the technical point of view, and to also be compliant with the GDPR. And here there's a balance to find between technical robustness and ethical values. So when thinking about data scientists and what they have to do, we have in mind this life cycle divided in 4 main steps. The first step is to understand the context and the objective of the model you will have to develop. Then you will have to pre-process data, and it's a burdensome task, we know. After that, you have all the activities to develop your model, and then your job is quite finished, but you have to give your output, what you have done, to other people who will have in charge the integration of your model in the global AI system and its deployment in production. So when you see this life cycle, well, we can say that as a data scientist, you will have ethical question to address at every step, in fact. Fairness, you will have to deal with fairness at the beginning, but during all the process, and also for explainability. So once with that, the question is how to do. What tools do we have to do this? So let's have a look of the fairness principle. We'll start with a short state of the art, and then we go deeper in what IBM offers in his toolkit. So on a practical point of view, the question is what we have at our disposal to train fair model. Well, we have some metrics and some algorithm that mitigate bias in dataset. We have also some toolkits, and we have initiatives or label. Concerning the metrics and the bias mitigation algorithm, there's an upgrowing literature, and there are a lot of algorithms that are released today, but many are pending to be implemented in toolkits. And so we benchmarked some toolkits. This is not an exhaustive list, of course, but we have the tool from Google, a what if tool, that is very convenient for people in charge of deployment or final users, because it offers visualization. It's a visualization software, and it's very simple and intuitive, but it's not the perfect tool for the data scientist. So we looked at Themis ML. It's a developer tool similar to AI Fairness 360, but it provides few metrics and an algorithm to mitigate bias. We looked at Equitas. It's a tool to test ML model and different discrimination definitions. And finally, we decided to focus on the toolkit developed by IBM, AI Fairness 360, because it was the more complete. And you have also initiative of label, such as Matic, who developed a fair data use label. It's an automatic audit detecting the source of discrimination in the algorithm. So let's have a look of the toolkit from IBM, AI Fairness 360. So it's an interesting toolkit because it's a bit different from the other toolkits because it provides metrics plus the way to mitigate bias with the different algorithm. You have 60 metrics to evaluate unfairness in your data set, the data set you will use to train your model. You have, at the moment, it's always moving, but at the moment you have 11 bias mitigation algorithms. We will see them, well, the principle of them later. And it's an open source toolkit with a license 2.0 Apache. You have the complete API available, and it's a Python package. So the tool is very rich, but the scope, it's important to say the scope is limited to binary classification on structured data sets. Well, I say in introduction that I will give you a global view, an overview, so we won't go deeper in mathematical formulas, but some definitions to understand what will follow. Well, we have the true label that the model tries to predict, and it can be favorable or unfavorable, that's life. You have the predicted label, that is the output of the machine learning model. And you have what we call sensitive attributes. It represents the groups for which there is unfairness, for instance, race or gender. And as we are in binary classification, the output of these sensitive attributes can be 1 or 0. And for instance, if we think about race, if it's 1, it means you are white, and if it's 0, it means you are non-white. Very simple. And you have the features, of course, that are used in the training data set as an input to train the model to make the prediction. Saying that, when we think about fairness, we have mainly two types of fairness. You have individual fairness and group fairness. So individual fairness was introduced by Dwork, and well, the idea is to treat similar people similarly. And there's a metric that have been defined by Zemel called consistency to measure that individual fairness. And the formula is, as you can see here. And the idea is to compare classification prediction of one input you are interested in to the classification prediction of its k nearest neighbors. Then you have the group fairness. For group fairness, well, you have a notion called disparate treatment. The idea is not to use the sensitive attributes at decision time. The prediction should not rely on sensitive information. And therefore define a model free of disparate treatment as predicting the same output after observation of the sensitive attributes given the non-sensitive features. It means, for instance, if we take the example of race, if you are applying for a job, if the model is fair, whether you are white or non-white won't have an impact on the output, on the prediction. This is a notion, but there's no metric associated to this. Talking about metrics, in the group fairness, we have two metrics. You have the disparate impact and the disparate mistreatment. Disparate impact, the idea is each sensitive group has the same global ability concerning a task, a decision, the same fraction of favorable classification. And the perfect value, of course, is 1, but 80%, the 80% rule is often used. And so if you have a disparate impact between 0.8 and 1.25, it's acceptable. So the idea here is a global fairness for different sensitive groups. And you have another kind of metrics. It's a disparate mistreatment. Here, the idea is that each sensitive group has equality of accuracy and calibration measures, and the perfect value is thereby 1. In fact, it depends on the context, on the objective of your model. For instance, if we are in the health domain, we will privilege the disparate mistreatment. If you want to predict the occurrence of cancer, for instance, you will choose the disparate mistreatment. You want the prediction to be to have the same accuracy for any group. If it's for how can I say, a student applying for a university, perhaps you will choose the disparate impact, because all students have to have the same chance to go in the university. So it's really context dependent. So I said that AI Fairness 360 is very rich. So let's have a look of what you can find in AI Fairness 360. You will find the metrics and the algorithm to mitigate bias. And I said at the moment you have 11 algorithms. So to help you, Hugo, our internship, developed this decision tree, based on the Equitas decision tree. Equitas produces a tree like this for metrics, and so here we produce this one for to help you identify the most convenient, relevant algorithm to use. So depending on what you want to privilege, disparate impact or disparate mistreatment, and if you want to use your data set for other tasks or no, and so on, you will use some algorithm or not. And as you can see here, well, the idea is not to go in details in this decision tree at the moment. You can have a look after. But as you can see, there are 3 categories of algorithm. You have what we call the pre-processing, the in-processing, and the post-processing algorithm. So what is it about? Pre-processing bias mitigation algorithm, the principle is to use them before training your model. Often they refer to techniques modifying features on which the model will be trained, as discriminating decisions of the model are usually due to biased data. So the advantage of this kind of algorithm is that they comply with disparate treatment, also with disparate impact and individual fairness. They are not model specific, so you can use them anyway. And the modified data sets are usable for other prediction tasks if you need. The disadvantages are they cannot improve disparate mistreatment because you have to choose in group fairness, either you privilege disparate mistreatment or disparate impact. You cannot manage both at the same moment. And this kind of algorithm are less efficient than in-processing algorithm as they are not specific to the classifier you will use. The in-processing algorithm, so the principle is to use them while you are training your model. And the advantages are they are often efficient to reduce bias. You have a great control on the balance between accuracy and discrimination and fairness, let's say. Group fairness and individual fairness are taken into account. Are the fairness only intervenes during the training. So two similar individuals will be predicted similarly at prediction time. And the disadvantages, well, they are usually model specific. And the implementation done on AI Fairness 360 needs the sensitive attribute to operate. So one need thereby to remove the sensitive attribute of the dataset before prediction time to comply with disparate treatment. And you have the post-processing bias mitigation algorithm. So you use them at the end when your model has been trained, and they modify the predicted labels to comply with the fairness definition implemented. So they are not specific to, well, they are not specific to one classifier. That is an advantage, but they have disadvantages. They do not comply with the notion of disparate treatment. They all need the sensitive attributes at decision time to modify the labels. They do not comply with the individual fairness, as they do not use the non-sensitive features to change the label. And you have no control on the fairness accuracy trade-off. So as a takeaway, I can say about AI Fairness 360, well, it helps you, it's a toolkit that helps you evaluate the fairness of a model. You have metrics and an algorithm to mitigate bias, and you can choose either to privilege individual fairness, so to treat similar individuals, or to privilege group fairness. And here, depending on your context, you can privilege what we call disparate treatment. So prediction should not rely on sensitive attributes, and you can choose the disparate impact, which means each sensitive group has the same global ability. It's concerning a task, or you choose to privilege the disparate mistreatment. That means each sensitive group should be predicted with the same accuracy. And once you have chosen what you want, what kind of fairness you want to privilege, you choose one of these algorithms, and you can use them either before training your model, during the training phase, or after the model have been trained. And this really depends on the context of your development. After fairness, well, I said at the beginning that we focused on fairness and explainability. So what about explainability? So why do we focus on explainability? Because, well, to achieve an ecosystem of trust, trust cannot be achieved without explanation. If you don't understand something, you cannot trust it. It also helps to comply with the incoming regulations. And we know that today, especially in deep learning, models are deeper and deeper, and thereby less and less human understandable. And well, on the left side, you can see that, well, if you have a model that is explainable, you can trace all the actions that have been done. You have the ability to be transparent about the system, its behavior, its outcomes, its training process. So if you have an audit, you can provide the proofs, and you can be accountant and ensure your responsibility as the developer of the system, and you can provide the proof that everything is compliant with what have to be done. So previously I said that the kind of fairness you want to privilege depend on the context. Explainability is also context dependent. Because depending on the person you have in front of you, the explanation you will give will be different. And that will depend on the recipient, the impact, the regulation context, and the operational context in which you are developing your AI model. Indeed, depending on the background of the recipient, for instance, if I have to explain my model to a data scientist, I will go in details. If now I am an employee in a bank and I have to explain my client why I refuse a loan for him, the explanation I will give will be really different. So you have to adapt to the recipient of the explanation, his level of expertise, and also the time he has to receive this explanation. The explanation depends also on the impact your AI model will have. Will it possibly harm the person or not? And explanation can mitigate the harm? It also depends on the regulatory context, of course. Is there a risk to infringe fundamental rights or not? And that's why today the European Commission is talking about risky AI. And you have also to take into account the operational context. Is explainability an operational imperative? Is it compulsory for safety certification? Or usability needs. For instance, if you are developing an AI system for health, it's quite risky. It's not the same level of risk as in another context. So you have to take into account all this to choose the kind of explainability you will give. And explainability depends also on the type of model you choose. As you can see on the lower side, the more accurate is a model, the less interpretable it is. You have the linear regression. It's quite easy to understand for us as a human, and at the other side you have the neural networks. Very complicated and called the black box because they are very complicated and it's impossible for a human to understand their behavior. And this is the situation today on the left side. And of course, on the right side, you can see the desired situation. We want the model to be always accurate, but to be more explainable and perhaps and this is the challenge, in fact. So we have various different type of profiles of people that could receive explanation. You have, of course, the data scientist. Explanation will be helpful for him to improve and debug his system. And at the moment, it's it's the way people are using explainability in AI. Most of the time, it's to debug the system. And it will be also useful to facilitate testing for safety standards. For the product owner, explainability will be useful to understand the global behavior of its product, what is optimized and how it is done, because he has a responsibility as a product owner. It will be helpful also to provide limitations of the system, the potential harms of reaching the limits and how it can be mitigated. The people who are in charge the deployment, the integration of the AI model in a more global AI system will need explanation to position the model in the overall system's operating environment and to understand its limitation and range of efficient operation. We can think of the potential of drift, of the model. So if you do not understand the way the model can be used, there's a risk to see the model drift and that the output of the model won't be as accurate as before. For the auditor, the regulators, explanation will provide the ability to audit the whole system or a particular prediction, depending on what they want to see. For the system user, by system user, I mean, for instance, the employee in the bank who is using at the end the AI system that have been developed by the data scientist. He has to trust the service he is using, and what might be done in case of unforeseen situations, and also he has to check that the system works appropriately and to enable meaningful challenge. And the end user or the affected person, if you are asking for a loan, for instance, you have to understand what are the factors affecting the decision, and you have to be able to understand if you are treated fairly and to potentially challenge the decision. You have also a different kind of explanation. So the good news is that there are tools behind those definitions and those type of recipient and those type of explanation. We have tools. But the good news. So what kind of explanation we can choose? You can have local explanation or global explanation. Local explanation, it's the ability to explain one particular outcome. You are asking for a loan, and the employee from the bank say, no, I'm really sorry, but no, we cannot give you this loan. You want to understand why for you. On the contrary, you have the general explainability. It's the ability to have a global understanding of the whole process of the model. For instance, an auditor will want to have a global explainability. An end user wants a local explainability. Then you can have a post hoc approach or explainable self-producing system. Post hoc approaches are methods that try to explain a model already trained after. Versus you have some explaining model that are directly interpretable or self-explaining model. They generate themselves, if I can say, explanations. And you have also explanations that are model specific or model agnostic. You have methods that are only suitable for use by a single type of model, for instance, neural networks, versus techniques that can be used for many different types of model. If you want to go deeper, you can click on the link. So I say it's good news because we have a lot of tools. So again, this list is not exhaustive, but as you can see on the left side, you have a list of toolkits available. You have the toolkits for self-explaining model or directly interpretable and post-hoc. And in the post-hoc category, you have the local and the global. And well, as you can see, AI Explainability 360 is the more complete toolkit. That's why we decided to go deeper in it to see what we can use. So in the same idea of a decision tree, so this is a decision tree from IBM. As you can see, you have around more or less 10 different type of model, explaining model. And depending on what you want to do, you can use this decision tree to guide you in your choose. So do you want to, if we are looking at the right side, do you want to understand your model? Okay. Are you looking for local or global explainability? Do you want a post-hoc or a self-explaining? Or do you want direct or post-hoc global explanation? Depending on, again, the recipient, you will choose a local or a global approach. And depending on the model you are using, the AI model, you will choose post-hoc or self-explaining model to explain the output of your model. So I decided to illustrate here, not all of them, but some of them. Here it's a global direct explanation. So I choose a data set called adult, and the prediction here is either you will earn more or less than $50,000 per year. And the predictive model is a generalized linear rule. And here we use the explaining algorithm GLRM. So we are in this category here. We are in a global direct method. And the accuracy is 85%, so it's quite good. And well, the goal of this explaining algorithm is to explain the contribution of each feature to the global prediction. So here you have the different features, capital gain, for instance, education number, capital loss, and so on. And here you have coefficients. It's a binary classification. And so the higher is the coefficient, the more important is this feature for the predictive model's final score. And if the sign is positive, it's a positive influence, and it's negative, it's a negative influence. And automatically, the explaining algorithm created new features, single, like this, or multiple condition rules have been learned by the explaining algorithm. And these rules are added to the original features as an input of the generalized linear model. And it helps us as a human to understand the output. If we have a look at hour per week, here, hour per week, it's the original feature. And as you can see, the model created another feature, hour per week, less than or equal to 40 hours per week. And here in the graphical presentation, you can see, well, in orange, it's not the exact transcription, but it's to give you an idea. Without this explaining algorithm, we will have we'll have no information to understand deeply. Thanks to this GLR explaining algorithm, we can see a discontinuity before and after 40 hours per week. That means that this is this changes the output of the model. This is a key feature. Another example. Now we skip in the local explanation, and it's a local and post-hoc explanation based on features. So his name is Shap. It's quite close from a very well-known called Lime. So the idea is here is to find a simple and interpretable surrogate model, something local, that best approximates the complex model around a specific observation. So here it's always the same data set, of course. So the prediction is, will you earn more or less than $50,000 per year? So for this instance, the probability at 45% is yes, you will. And the goal of Shap is to give you explanation and how to read this. So here you have this straight linear vertical line that indicates the model average prediction over the training set. And here you have the most important features explaining the prediction for this person. And you start from the bottom, and you can see the accumulated effect of all the features to arrive at the final result, at the final prediction. So as you can see, the fact to be non-diverse has no impact. But here, race, so this is important. As you can see, race 0. So into bracket, it's the value. 0, it means that the person is non-white. And native country, Philippines. So the person is from Philippines. It's interesting because being non-white and native from Philippines contributes positively to the final score. You know, it's like when we were a kid. Oh, it's blue, it's cold, or yes, it's red, you are approaching the target. The idea is like that. When you go this way, it's the positive, this feature contributes positively to the final prediction. When you go on the left side, it contributes negatively. So here, the fact to be non-white and native from Philippines contributes positively to the final score. It's interesting because we trained the model before running this explaining algorithm. We trained the model, and before we used the pre-processing bias mitigation algorithm I presented you before. And we can see that now the model is fair. It's a proof that the model is fair. Here, for instance, another example, as you can see, it goes on the left side, so it's a negative contribution. So let's see what it means. Work class private 0, it means that the person is not working in the private sector. So working in public sector contributes negatively to the prediction, earning more than $50,000 per year. And education number, this person has 13 years of education, and it contributes positively to the final result. another example of local post-hoc explanation, but based not on the features, but on samples. And you have this one, proto-dash. So the idea is, I have this person who is predicted positively to earn more than $50,000. She's 46 years old. She has 13 years of education. Okay, she's a man, she's non-white, etc. And this is a similar observation from the training data set. As we can see, they have quite the same level of education. They are both men, they are non-white. They are working the same number of hours, but they haven't got the same age. So it means that when I see that, I say, okay, age have no impact on the output. It's not a prediction. And finally, you have another algorithm called SEM. It's also local. It's also post-hoc. It's also well, it's based on features. And here the idea is that the algorithm has created an observation, an instance that have well, the prediction is the contrary from the one you are looking at. Here, it's a people, she's 26 years old, and she's predicted with 60% of probability to earn less than $50,000 per year. And this one, it's not a real person, it's created by the model, is predicted to earn more than $50,000. And you can see, well, globally, they have the same number of years of education, but this one is older and he's working more hours than this one. So by these examples, if we just come back to the decision tree, yes, this one. Again, it depends on the context and what you want to explain, and it depends also on the model, the AI model you will use. As a data scientist, with your expertise, you will choose the explaining algorithm that suits the best with what you want to do. So to conclude on explainable AI, it's a must-have for trust, for adoption, to help to have traceability, to be transparent, accountable, and auditable. It's context dependent. It depends on the person who received the explanation, on the impact, the human impact of your AI system, the operational impact also, the regulation context, and the time you have to explain and to receive the explanation. The majority of explainable AI is a bit higher than fairness AI. And you have different type of explanation, local or global, intrinsic, self-explaining, or after the training of the model, post-hoc. And you have explaining algorithms that are model agnostic or not. But it's still in its early age, and SHAP and LIME are the more popular one. But as we just seen before, there are many other type of methods to give explanation to the model you have developed. And that's it for this overview. So do not hesitate if you have any question.
Oh, this was a great deep dive for me in fairness and explainability. And my first question is, I mean, you work for Orange, and I mean, if this ever comes into use, Do you think there needs to be a new role like AI communicator? I mean, it's so difficult to tell this to a normal person, like to communicate what you just showed to a employee, to a user who's non-technical. Do you think there needs a new communication role? Like you understand, a person who communicates?
Well, I reformulate your question to, do I think that, well, it's not simple to understand, and do we need somebody in companies to
communicate, like what you say,
to communicate, to explain?
And then communicate, like when to like a bank employee who has to explain it to. How you see that? I mean, can you just, needs there be a role in the middle, like a person who explains that?
Oh, but the idea is to, as we saw, if you, well, you have method to explain the behavior of a model. Well, global explanation is for experts or for auditors or the product owner. For the end user, you have to choose a local explanation. And by the examples I shared with you, we saw that comparing you with the closest person, but who has been predicted differently from you, is a way to explain, or to with SHAP also to explain the person what kind of features had an impact on the prediction is very useful. But it's true that SHAP, for instance, if I show the condition, the dependent plot to a customer of a bank, he won't understand. You will have, as a bank employee, to explain him, or to you will use this to give him explanation.
Yes.
So I can say that we are at the beginning of this story. We can see that personally, SHAP, once you have understand how to read this plot, it's quite interesting and simple to understand. Or comparing myself to a similar observation predicted differently or identically, I can also seems to me easy to understand. And I think that at the end we will have some tools, yes, and more, I hope. And it's our expertise that will make that we will choose one or another depending on the context, I guess.
Yes, thank you. So now I have more people want to ask some questions, and I thank you very much for this good answer. Here comes a compliment, Kai Firschau. Thank you very much for the fantastic presentation. I've visited several presentations, ethical design, and this was far the best, most informative and practical oriented presentation. Thank you again. I would love to hear further talks from you in the future. Best regards from Germany. And that is the question, not really formulated, is how can people come back to you? Can they just write an email to you if they need more information? Oh, I lost you. You hear me? You hear me? Right, one moment.
I didn't understand the end of yes, but yeah, my
Hello?
Ah, yes. Yes, I can hear you. Yes, you can hear me?
Yes. Super.
Yes. Yeah. Do not hesitate to contact me, and me and my colleague, we will come back back to you.
Great.
And it will be interesting to exchange with people, because it's quite new, and I think it's a quite exciting period, because well, it's not new to say that science cannot be done without conscience. It's from Gargantua, from Rabelais, but today, with the power of AI and the presence of AI in our daily life, well, skipping from the principles to practical things, it's now. It's not for tomorrow. It's for today, and it's very exciting to work on that. And so we talked about metrics for fairness, but there is no metrics for trustworthy AI, for instance. We're talking about that on the European context, but what is it? Trust, it's to be fair, to be accurate, and to respect law. Okay, so how will we measure that? Well, that could be an interesting question to talk about, for instance.
Yes.
So yeah, do not hesitate to come back to me.
Yes, because I see many questions here, and our time is running out. So if your question is not now basically answered, please just write directly to us, to Crystal, and if you want, you can also write me, but you see the email. And one more last, and then we have to go. Can explainability of an AI system, this comes from Janos Tolias, can explainability of an AI system in medicine reveal hidden risks in AI medical predictions that cannot be otherwise revealed? Could that,
what?
Like, can explainability of an AI system in medicine, the use case is medicine, reveal hidden risks in AI medical predictions that cannot be otherwise revealed? Would you have an answer to this? And if so, what type of explainability would be more appropriate in this regard? So,
about explainability, I'm not sure to understand in details.
The question is, in the use case of medicine, could a software, can explainability, like a software, reveal, also find hidden risk in medical predictions done by AI, like predictions like AI system would predict, take this and this, no? Could this software you showed, could that reveal hidden risk in medical, you think, in medical predictions?
Well, I always say that in the medical field, yeah, we have to produce explainable system, but also fair system. So I guess that if the model is fair, it will eliminate, if I can say, most of the risk, because we are human and we are biased. And if we choose the good metric before choosing to develop an explainable model, before that, if we say, okay, my model have to be fair, and what kind of metric do I choose? And here in medicine, the idea is to have the same accuracy for anybody, any group. So you find the group fairness, and you choose, sorry, the disparate mistreatment, I guess, and then you explain what your model have done. I guess you will be ethic and will respect those principles.
Mm-hmm. Yeah, I think it's because of time, I could now ask you many more questions, but I will not. Thank you very much for this answer.
Thank you.
I'm very happy you have joined us today. This was very, very great overview about the different tools out there in the moment. So thank you very much. And I will send you the recording. You, Crystal, will get the recording, and you will be the person to decide if it will be published. And if so, then it will be on the YouTube channel. So
Okay.
I thank you. And now I want to invite everybody back next week to the cafe. It will be with Stefan Göllner, and I'm happy to send you again an invitation. His session will be about AI Campus, the learning platform for artificial intelligence. You will get automatically this invitation when you're here in this session. Thank you very much and have a nice afternoon. Thank you, Kristen.
Bye-bye. Have a nice afternoon. Bye.